Hey class, Adam Ward here. You are watching the second of 4 videos about turbulent pipe flow. In the first, we introduced the Moody diagram and did some dimensional analysis. And what we're going to do in this video is work through what I call a type 1 problem. Type 1 are the problems that make me happy because they're the most straightforward. What I call a type 1 problem means that it's a problem where you don't know the head loss. And so we're going to use the Moody diagram to solve such a problem. So the general setup for a type 1 problem is this. You know something about the flow, so probably the diameter or the flow rate or the velocity. You know the fluid properties, so density and viscosity, and you know something about the pipe geometry, meaning the diameter and the roughness. What kind of pipe is it? And so the head loss is what you don't know. And the methodology, the right-hand side of the screen, is more straightforward here. Find your Reynolds number and your relative roughness. Use the Moody diagram or one of the equations to find your friction factor. And you can calculate your head loss straight away. So let's see this in practice. What we're going to revisit here is a problem that we've done in the past. This is about the Alaskan oil pipeline. So you've got information given to you about the flow rate in the pipe, density, viscosity, a diameter of 1.22 meters, and a relative roughness of about 0.15 millimeters, meaning that the average grain or roughness, if you will, the average grit on the inside of the pipe is about 0.15 millimeters high. And what you'll recall is that in this pipeline, you've got pumps that are spaced regularly through the pipe in order to basically add back in the energy that gets removed from friction loss. And so we know that at the inlet of a pump, you've got a pressure of about 400 kilopascals. So on the upstream side coming into a pump, like 0.1 and 0.3 in the diagram here. And on the outlet side of the pipe, after you've added the energy, you're at about 8 megapascals of pressure. And so the question here is, what is the required pump spacing to keep this system operating? Or if we've got the system as shown in the bottom of the screen, how far apart are these pump stations? Do you need a pump every mile? Do you need a pump every 50,000 miles? What is that spacing to keep the system moving within the parameters that are defined? All right, so this is all your given information. And so this is a type 1 problem, and we might have identified that because you think, well, this is an energy equation problem, and I need the head loss for it. So some quick calculations of things that we know we're going to need. Velocity, so average velocity in the pipe, discharge divided by cross-sectional area, or about 2.63 meters per second. We know we're going to need the Reynolds number for a Moody diagram problem. And so I'm plugging in the given value for density of 910 kilograms per cubic meter, the velocity we just calculated, and the diameter given in the numerator, the viscosity in the denominator, and I get a Reynolds number of about 293,000. And because I know I'm taking this to the Moody diagram, where we're using a scientific or exponential notation, I'm going to go ahead and convert that to 2.93 times 10 to the fifth. Good habit because it just makes sure I'm using the right order of magnitude on a Moody diagram problem. The other thing that I'll need is my relative roughness. We had a roughness height of 0.15 millimeters. And you can see I'm going ahead and converting that into meters. So its units will cancel with the diameter of 1.22 meters in the denominator. And I get a relative roughness of 0.00012. Okay, so I've got a Reynolds number. I've got a relative roughness. Time to go to the Moody diagram. Oops. So first, I'm going to find my relative roughness, that epsilon over diameter, 0.00012. Now, that line doesn't exist, so you can see in red I've approximated where that line would be. Remembering that you're working on a log scale over there on the right. So I've sketched in that red line for the relative roughness that I'm working with. Similarly, I know my Reynolds number was just about 3 times 10 to the 5th, so I've drawn that blue vertical arrow at the appropriate location. I find the point where where my Reynolds number, I read up to my E over D line, or that blue arrow, I read it up until I hit the red, and then I bounce perfectly horizontally over to the left-hand side, and I'm estimating that friction factor to be 0.0157. You can debate with me about what I ought to have picked for that last decimal point, but that's the accuracy that you get with a Moody diagram problem. Okay, so with my friction factor in hand, now I can go to the energy equation. So if we can assume that this is a horizontal pipe with a constant diameter, the energy equation reduces to this, that the pressure drop is equal to the head loss, and of course we know that head loss is the Darcy-Weisbach equation. So if you're not sure where this equation came from, I would encourage you to start by writing P2 over gamma plus Z2 plus and so forth, and on the very last term on the right hand side you should have had a minus head loss, and then you would simplify that in accordance with the assumptions that we've made, a constant diameter and a horizontal pipe. Okay, so we've got this equation in hand. The delta P over gamma equals head loss. That came from the energy equation, or that simplification of what I've written in pink. The head loss side of it is using the Darcy-Weisbach equation. So we are in good shape. You can see what I've written now on the left-hand side is our pressure drop from 8 megapascals on the downstream side of the pipe to 400 kilopascals on the upstream side of the pump. I said pipe, I meant pump just a moment ago. And so we're writing this equation from the outlet of one pump station to the inlet of the next. So that's our pressure drop in the numerator. And in the denominator, I wanted specific weight. I wasn't given specific weight in this problem, but I remember that specific weight is density multiplied by gravity. And so I've gone ahead and used the given density and gravity there. On the right-hand side, I've got my friction factor, 0.0157. I've got my unknown length over pipe diameter, and I've got my velocity squared over 2 times gravity. And so I can solve this equation and get a length scale of about 1.88 times 10 to the 5th meters. And so what we've proven to ourselves in this problem is that you need a pump about every 117 miles or so. Right? So for the energy that is getting lost due just to the turbulence inside the pipe and friction inside the pipe, about every 117 miles you're going to need a pump that's able to add back in this amount of pressure. So I hope what you see from this example problem is 2 things. 1, practice using the Moody diagram so we can see how that works. And 2, you can see that what we've taken the energy equation and we're using the Darcy-Weisbach where we would have had that generic head loss term. And so you can see where that information from the Moody diagram flows back in, no pun intended, flows back in to our energy equation problems. All right, so this was a type 1 problem. This is the easier and more straightforward version of the world. Check out videos 3 and 4 for this subject, where we'll do a type 2 and then a type 3 problem, and we will start to iterate or guess and check. I hope this helps, and I'll see you in the next video all. Thank you.